All right, so thanks for all being here. As you mentioned, I was here last year, and we had a discussion of using dynamic taint analysis to look at post-crash analysis. So at the point of a crash, we were looking forward to see if a read AV could possibly be leveraged into a writable condition or an executable condition. And we were also looking to see what external user input caused the source of the crash. And we're going to review a little bit of those concepts, but if you don't have a solid understanding and grounding in taint analysis, I'll refer you back to the slides from last year. The big interest this year is in applying the symbolic execution portion, which is what we use to look forward from a crash, to other applications such as finding bugs and also doing some binary analysis, bin diff analysis. I just gave this talk for the first time 4 days ago at ShakaCon, so this is a brand new talk for everybody. And it's actually a good thing I have 10 extra minutes because I didn't even really get to the bin diff portion before. So this is pretty exciting. One thing I do want to talk about really quick before we get into deep details is this is an interesting technique that also not only allows you to find bugs originally from scratch using well-formed input, but it also lets you replicate or reproduce bugs that you just heard about and don't want to go through the effort of fully debugging and reverse engineering yourself. So 2 days ago, Don Bailey, actually, is this not up there? Of course not. Don Bailey found a bug in LZ4 and LZO compression. It's a 20-year-old bug that had never been discovered, and this is a compression algorithm that's used in the Linux kernel. It's used in libav, libffmpeg. It's used all over the place. If you run a Linux browser and you use the mPlayer default media plugin, you're remotely exploitable from this. And this bug wasn't found because it's triggered by an unusual condition in the compression file format, where there's actually a literal that lets you specify that the next series of bytes are actually not compressed at all. So it has a feature that allows you to put non-compressed data inside of a compressed package. And so last night I was really excited, and I had this idea at like 7 o'clock just before I went out to the party, and I decided, well, wouldn't it be cool if we could get this to trigger overnight? And sure enough, came back last night about 4 o'clock in the morning, and it was really exciting times because it took about 3.5 hours, and I was able to trigger this bug. Now, unfortunately, you will see that there is a subtitle on this introduction slide that says, "Never RM at 4 a.m." What I had done is I had copied the crashes directory over, and I thought I had copied the crashes directory over, removed it, and went to replicate it. Well, as it turns out, I had actually copied the binary instead of the directory. So there will be a blog post after this, like in 3.5 hours or so, that will show you that we were able to reproduce that. But don't worry, there's 2 live demos. You'll be able to see it in action. This is a pretty opaque process. It's fully automated anyways, so it would have been a matter of looking at the crash dump. So a blog post that fully describes it will be a bit better. But as a reminder lesson to everybody, never RM at 4 a.m. Let me get this back into presentation mode. There we go. So what we're talking about in general with the system for automated vulnerability discovery, and I've had some talks before that were semi-automated vulnerability discovery, assisted model development, things like that. But truly, this system is 100% automated. You give it a well-formed input and the ability to observe the execution of a program over time. And what our goal is to generate new test inputs on the fly. And basically, there's multiple approaches at automated test generation, but the idea is essentially that what we want to do is achieve execution at all locations in the code graph, which really means an exercise of reachability of the graph as well as reachability of the data constraints that allow you to travel to the different portions of the graph. There's basically 2 main approaches to this. Of course, we're all probably pretty familiar with fuzzing. Whether you like it or not, fuzzing is a zero-knowledge approach towards finding bugs. And it's a low-effort, simple system where you can take a well-formed input, mutate it and modify it in any random number of ways, and produce malformed input that may perhaps produce a crash. There's different approaches at this. There's the zero-knowledge mutation. There's syntax model-based grammars, where you might use something like Protos or Codenomicon does, where you generate a BNF grammar that describes exactly the different structures and data types that are in a format, and then it mutates the grammar itself so that it would generate new malformed inputs. You can, of course, interrogate APIs directly, where you're sending edge values on integers or malformed strings with character codes, percent codes, trying to trigger format bugs and so on. But what we're really interested in today is something called concolic testing. And that is the system that is designed around observation, translation, and mutation of the branch logic and constraints that are executed during the first round of parsing an input. So the better fuzzers that you see out there now actually are able to infer grammars. So rather than have to do what Protos did, where you're syntactically encoding the format of the file structure, there's ways to use things like n-gram analysis and different types of string grouping. And when I say string grouping, this is symbolic string grouping, so any sequence of bytes. And you would take a large corpus of files and you would look for fuzzy pattern matching within those files to try to identify object types or object headers or something like this. And this does apply really well to even PDF file formats and complicated, complex structures, whether it be even a string type language where it's JavaScript or a binary language where it would be structured data. A really good example of this is also from the Oulu group, which was the guys that made Protos and later Codenomicon. There's a tool called Redanza, and it has about 30 different algorithms for doing automatic structure inference. And it's one of the primary fuzzers we use in our fuzz farm at work. And it's a good approach, but it has its limits, which basically that when you have a series of constraints on an input, a certain amount of fuzzy manipulation of that data is only going to reach certain known edge cases. You know, if we're trying to trigger integer overflows, we're looking at the edges of signed values or unsigned values that will hopefully get multiplied or added together and wrap over and so on. But when it comes down to fuzzing a file where you don't have a certain type of data structure inside of it, like if you're fuzzing a MP4 or a movie file and you don't have the tag for the structure that you're interested in fuzzing, well, you're not going to generate that tag randomly. You're not going to generate new data types from a single well-formed input. You're going to be able to mutate well-formed input with the types that are inside of it, but you're not really going to be able to discover new types of structures and data types without analyzing the code itself. So this is a canonical example that's used in the original white papers that came out from academia, where it's simply there's an exact 4-byte value that must be found to hit an error condition. Of course, we know that 32 bits would be 4 billion attempts to actually be able to reach this simple condition, and I'll be able to show you here in a little bit how easy it is for our tool to find this on the fly. So anything beyond string grouping algorithms, we need to have a system for instrumenting the code so that we're able to observe it. We need to be able to follow data through the process so that we can see where external input interacts with conditional constraints inside of the program that allow you to take one branch versus the other. And then we need a system for tying that all together in order to solve those constraints and be able to interpret what those code branches mean and modify the input data. So early academic work in this area was done by Patrice Goldfried, who is currently at Microsoft Research. And it's slipping my mind right now which university. I think it was Stanford that he was at before. And they came out with the first paper called DART, Directed Automated Random Testing, in 2005. And this was a system for doing exactly this, only it was limited to, first of all, it randomly chose a single constraint to modify, and I believe this system was source code only, one of these two were. Qt was the follow-up to that in the same year, And then finally, XE was produced by Dawson Engler's group, and this is the group that ended up producing CLE, if you're familiar with CLE today. So these were early approaches, but they lacked the scalability and the applicability that later research that came out of Microsoft was able to produce. Primarily, the main system flaws here were not taking advantage of the symbolic reasoning in an efficient manner, so they were spending way too much time trying to solve the constraints and not producing as many outputs as we'd like. So, I mentioned already taint analysis. I'm sure most people in this room, have at least done some code coverage before. There's several different ways to do code coverage, but the idea is that we're looking to collect the executed graph over the lifetime of a program. So when we're talking about the graph, of course, we have our basic blocks as your vertices, and your edges are your jumps or calls. And there's several approaches to doing this. The native debugger API is always an option, whether it be ptrace or debug API. But you have problems with that because you are running into exceptions or interrupts that switch from user mode to kernel space every single time you do a breakpoint. And in our case, we're having to do basically the equivalent of a single step. So we need a more efficient way to do that. CPU branch interrupts is a way to change the trap flag into, instead of doing a single interrupts or single step, into doing a basic block trap. And that would be okay, but we don't just need code coverage, and it's really not really exponentially faster. It's only faster just because instead of single stepping, you are getting each basic block. But as I mentioned, we need every instruction anyway. Static binary rewriting, I think, isn't there a talk tomorrow maybe on static binary rewriting? There's been a lot of research in this more recently. There's a lot of limitations to static binary rewriting, a lot of it having to do with indirection and being able to write back out a file that you've injected in many, many more instructions than just a single set of function hooks or whatnot. And then finally, dynamic binary instrumentation. That would be your pin toolkits or your Dynamo Rio, your val grinds, things like that. Taint analysis, it was mentioned yesterday in the GraphDB talk a little bit, but really what taint analysis is it's a method to track from source to sink the data flow as it executes throughout the program. And we're talking specifically about dynamic taint analysis in this case. You can do it statically, but we're interested in, during a single well-formed input parsing routine, where does that data go? What are the relationships? And so the basic model of this is that every instruction where there's data flow inside the single instruction from a source operand to a destination operand, you create a tree of dependencies. And when a source operand is tainted or otherwise influenced by external data, you propagate that level of influence to the new memory location or register that you're interested in. And so this creates a very, very large graph of dependencies, and you negate those dependencies or just forget about them once a untainted value is moved back into that register. As I mentioned, this goes into quite a bit more detail in my other set of slides. It's pretty old hat these days. There are public tools available that will get you where you need to go with taint analysis. We use the BAP framework, which comes with a pin tool that we've added some patches to and modified a bit for our purposes, but off the shelf it does taint analysis pretty well. There's also a library called libdft if you're interested in implementing your own or extending a pretty well-designed library that's self-contained. They have a limited x86 implementation. It doesn't really get into the floating point or SSE or anything like that, but it's really well structured and pretty efficiently designed, so it's a good model to build your own off of. Oh, and then of course there's BitBlaze, and BitBlaze is related to BAP. That was the original project, and it has a backend called Vine. BitBlaze used QEMU modification to the core. So if you wanted to look at other architectures like ARM or whatnot that's supported by QEMU, it might make the most sense to modify the QEMU core because they already have a lot of the internal code there. You would just have to hook the right instruction and then output a similar format. So DBI, why are we using DBI instead of static binary rewriting or the single stepping? It's simply the most efficient way that I'm aware of, and I think that most people are aware of, for doing very intense modification of a program. When we're talking about modifying and adding callbacks after every single instruction so that we can track this taint data, we need to really be able to do this as efficiently as possible. And what DBI does is it's essentially a JIT and from x86 to x86, where when you load a module into the process space, it disassembles it as well as it can. It tries to do call graph recovery, and every time an entry point to a function is hit, it does a control flow graph disassembly as well, and allows you to traverse that control flow graph on an instruction or block level and add instrumentation as you like. You can insert instructions or function callbacks, or you can purely modify the code on a block-by-block basis. And what happens is they copy this modified block of code into a code cache, and instead of referencing the original module every time you would jump to that code, you actually reference the cached modified version in memory. So basically, we use this because it skips problems with other methods, and it's pretty straightforward. Dynamo Rio is a little more efficient, but Pin seems to be the tool of choice simply because it's got a kind of a nicer API, and there's more code out there for examples. So the next part is symbolic execution, and this is where it starts to get a little exciting because this is where we get to let the computer do a lot of work for us. And the idea here is that symbolic execution is a algebraic form of formal logic that allows you to represent the execution of a program or the series of instructions in a program in a symbolic manner. And so what this means is rather than have to have literal memory addresses or literal values in your code, you can reference symbols. And this solves a lot of problems with things like indirection and the ability to reason about what the function of a code is. It's like a style of emulation that doesn't require you to have absolute values. And so, for example, when I was saying last year, when we were looking forward from the point of a crash, well, you can't really do that in an emulator or a debugger. You can't say, oh, we'll step forward, because obviously you corrupted memory. You need to be able to turn that corrupted value into a symbolic variable, something that could be any integer value. If it's a D word, we know that we cause it to be some over 2 gigabyte D word that allowed us to cause an integer overflow or something like that. So it's referencing off in the middle of memory space, unmapped memory, and so you can't step forward in a debugger. So we turn that into a variable, just like an algebraic variable, that could be any value between 0 and 4 billion, the size of a D word, and you build a formula that continues to use this variable rather than use a constant value. So here's an example of what it would look like to translate the canonical example from the left side, which is standard C code, into a formula that would be solved by a symbolic solver, SMT solver. Essentially, you have your declarations of variables, just like you do in C. You have conditions that you assert, so that would be like assignments. The ITE is an if-then-else, which is the same thing as an if-then-else in C code, where you're looking at certain values. In this case, you're looking at the offsets in the array, and you're checking it against this is the decimal value for those characters. And if so, then it will increase n plus 1. So it's pretty straightforward. It takes a little getting used to, but the syntax isn't too hard. Now this is a pretty obvious one. We can just look at this and know what the answer needs to be. There's not really a range. There's just an exact set of values. Here's another example where we can set an end condition. We translate the code into this SMT formula, and we set an end condition where we say at the bottom there, we assert that ret equals 1. Well, ret can only equal 1 if x is greater than 50. And in this case, x actually, I typoed a little bit. It should be x is greater than or equal to 50 on the left. But you can see on the right-hand side there, we've encoded the logic of if x is greater than or equal to 50, then ret equals 1. If x is less than 50, then ret equals 2. And we tell the solver, we want to know how to get ret equals 1. And so it would be able to solve this. Now, you have to imagine, of course, that this is obviously a really, really simple example. When we're talking about code parsing and millions and millions and millions of lines of assembly instructions, we're translating not from C code, but from assembler over to symbolic expressions as well. So as I already mentioned, last year we used the symbolic execution to look forward from the crash. So here's a contrived example, but you can see there where we assign a value to x and we dereference off into the middle of memory. So clearly we crash right there. But then we see what we're looking for is that was a read AV. We're looking to see if we can get to a write AV, which is in case 4 on the right here, where stack y equals 1. And so this is a little more complicated if you look at it because it's got some recursion in there and it's shifting values and it's not quite as obvious how you would get to the input state that would let you reach the case 4. And so what we do is we convert this to a symbolic expression that solver iteratively goes through and basically every time this branch happens where it's recursively calling back into exploit me, we're re-encoding that logic into the solver. So you get this tree of expressions that continues to grow. So every time that value is shifted, it's a new code that's getting exercised. And in the bottom left there, it's all right, you're not supposed to be able to read this, but bottom left you can see there's that green circle, and we were able to reach a tainted write symbolically through emulation. So you can look at the slides from last year. This code's already available. And by the way, all this code that we're talking about today is fully available. But the idea is just to show you the power of symbolic execution, where you can emulate forward. You can turn static constants or memory references into a range of references, all possible values for that data type size. So the last thing that we need to think about is what are the constraints in the code paths that we're encoding into these formulas. You know, obviously, if we want to reach one block versus the other, and our input only got us to a small set of the code coverage, we need to figure out what were the constraints that would have allowed us to get to the other part of the code. So obviously, when we have branch conditions in x86, we're looking at the flag. One of the flags for whether or not to take the true or false condition, depending on what type of branch it is, if it's greater than, less than, so on. And then somewhere up in that basic block of code, there was a comparison done that would have set the flag. And so we need to go back and analyze the blocks of code for which instruction actually determines the flag, what the flag was set to. And so that way we can modify the condition later so it gets a different range of values. So when I showed you that small example of x is greater than 50 or less than 50 and it takes one branch or the other, this is what we're looking for. We're looking for that comparison of is this register greater than this or less than this, and that determines which branch we'll take. So against binary targets, here's a simple example. We need to track the actual flags. It's not as simple as looking at the code where we're, when we're looking at C code, it was as obvious as the first SMT examples. Here we have to actually encode each of the semantics of every instruction in the assembler. And so it takes just a little bit more analysis. It's not as easy as just visually glancing at it. We have a whole system that's mostly supplied by the BAP framework. Once again, we've written our own symbolic executor on top of it, which the job of the symbolic executor is to convert from your code, which in our case is x86, to the symbolic expressions. And we do this using BAP because they supply an IR. So we go through a couple layers of translation, essentially. You go from your native target to an IR, and the IR expands out each one of the x86 instructions into micro operations. And this really makes it much, much simpler for us to generate symbolic formulas. Unfortunately, the formulas themselves can be more verbose and need more optimization because you are breaking out each instruction into micro operations. But we get basically a free semantic description of what each instruction does by using the IR. So finally, once we figure out which instructions in those basic blocks are the constraints themselves, we need to push that out to the symbolic executor or to the symbolic SMT solver. And so what we're asking the solver is we're putting that post condition on there. And as we create this gigantic expression that represents the whole code path, we're looking at each one of those constraints that were inside this expression. And we are flipping the condition. So rather than take the path that was greater than 50, we want to take the path that was less than 50. So we're going to go through and modify those constraints, generate new formulas for each modified constraint that we invert the logic on, and then we pass that out to an SMT solver so that it can tell us what the full sequence of input would have to be to reach that new symbolic logic representation of the code. And basically, all that said and done, what this allows us to do is get answers from a solver that says this is the input that would be required to take a different path in the code. So what does this look like in a kind of a more abstract context that is not in the SMT-lib format? It would be something like this. So in that canonical, let's see if I have that example again. In that canonical example, once again, we were looking for a precise set of bytes that was BAD exclamation mark. And we can see here that we have a formula that represents that the input, the first byte was equal to B, second byte was equal to A, third byte was equal to D, but the last byte was not exclamation mark. And so this would have been looking at the code and seen that the actual input took the false branch that said not exclamation mark. Because encoded in the assembler is an expression that says, if this is an exclamation mark, take true. If not, take false. We took the false branch, so this is the formula that we observed being executed. Now, from this one formula, we can see that we can negate each one of those conditionals sequentially. So in the first case, we generate a formula that says we want the 4 bytes to actually be correct, BAD exclamation mark. We invert that last condition from a not to an equals, and at that point, we will actually have the well-formed input that we want to trigger that error condition. But we don't know that, obviously. We just know that we have a symbolic formula. So we generate all possible combinations of formulas from a single run. So this allows us to not only save a lot of time in Taint analysis, where we only have to run one time and see the parsing of an input in order to generate a very large corpus of new inputs, essentially. So if you're 1,000 branches deep into a parser and you've observed the execution of this input once, we can generate 1,000 new formulas that we pass off to an SMT solver, and it will output us 1,000 new inputs that will reach different conditions in the code. Now, a bunch of these conditions will all get to an error state anyways. So, you'll generate 1,000 new inputs. 99% of those are probably going to be error inputs, but 10% of those just basically because the way that code can, like all 3 of these down here at the bottom would be inputs that don't matter either, but that first input would matter. So you generate a lot more inputs, but the point is that you don't have to do Taint analysis over every single one, and Taint analysis is quite slow. So we save a lot of time, and this is one of the big efficiencies that was a gain over the original research in Dart and Exe and Qt. Visually, you can represent this, of course, in a code coverage graph, essentially, and this would show where the input on the first condition can be B or it can be not B, and then you take the true or false branch, and it continues to iterate through the data constraints, and you can see at the bottom every permutation from an input that started as good, 4 bytes in a file, good, to the condition. All these new inputs would have been generated as the graph is solved, or the semantic interpretation of the graph of the code is solved, and so we would have generated, whatever, this like a dozen new possible inputs, and all of them would be passed through, and then one of them would cause a crash, and we'd go home with money in our pockets, right? So, Microsoft Sage. I didn't really do an intro. I myself, I'm the head of a security team inside of SourceFire VRT, which is now Cisco, and our mission is to basically find bugs, triage bugs, and mitigate them through more novel or at least the state-of-the-art techniques. And so I spend a lot of my time reading and researching what's the latest and greatest in academic research and trying to determine what is applicable in the real world. Well, prior to the last 5 years at SourceFire, I was at Microsoft, and I got to observe this process happen before my eyes, which is kind of an inspiration for what I do. And what had happened was Patrice Godefroy and David Molnar had worked on Dave Molinar's PhD together, and had released this paper called Automated White Box Fuzz Testing or something like that, Automated White Box Fuzzing. And what that was essentially an improvement on top of the Execute engines, and this was their attempt to take academic research and apply it at scale at Microsoft. And this happened in the Office 2010 and Windows 7 timeframe. And so their design took advantage of a lot of prior research that they've done inside of Microsoft. They have, one of the things that they do really, really well is in the MSR, they have some extremely good optimization teams. And so their platforms for the underlying systems that they use to pull this whole technique together are very efficient. So App Verifier, that's something that we actually all have access to. It's basically a debugger, crash debugger. For their tracer, they use something called iDNA, DBI framework. This, you may have heard of time travel debugging, or you might have heard of this tool because it's somewhat talked about outside the halls of Microsoft. But essentially, it's an extremely efficient runtime tracer that can do taint analysis and single stepping, and basically it records a deterministic forward single-step trace, and it has some really heavy optimizations. The papers are out there that you can read about. The optimizations are things like it analyzes the basic blocks ahead of time, so if the block's behavior is deterministic, it doesn't actually record every instruction inside the block. It goes ahead and just says that I visited this block, and then later on it concretely executes it. So it has the fastest runtime tracer I'm aware of, for sure. And this is something that I believe now the product security teams even sometimes hand out to people if you have a crash on your own system and you call them and so on. So I don't know the official word on that, but that's something I've heard. Then, of course, they have a system for playing back these traces. So this is all an offline and separate approach to doing each step here. So they have something called iDNA, or Nirvana, which reads the iDNA trace, and it's capable of doing a code coverage analysis. And it also has the ability to do things like trace system calls, and it has like a whole heap model and stack model, and it's basically like an emulator over these traces. And then they have a system called TrueScan, which allows them to do the taint analysis and includes the Symbolic Executor. And then when I mentioned the Symbolic Executor earlier, that's the system that converts the native code to symbolic language for the solver to solve. And then finally, they were the ones that wrote Z3, which is now publicly available. They used to call this Dissolver or something, but yeah, it's Z3 now. A little note about Z3. Prior to Z3, there was a solver called STP that also came out of Dawson Engler's group. It was specifically written for the XE approach, which once again is now CLE. So STP used to be the best that you could possibly get. We support both on the back end, and Z3 certainly is the more efficient one. They just have, once again, optimizations that are unmatched by any other solution. So their main contribution in their paper was a series of optimizations and a new way of doing code graph search. So as I mentioned, we generate a series of new formulas from a single observed execution. That was their primary contribution in the science of doing concolic testing. Before, people were doing depth first search or breadth first search, where they were looking at what was the last or first constraint involved in the formula, and they would invert that constraint, and then they would generate the input, and then they would observe it again, and they would do the same thing over and over and over and over for one branch at a time. So they took an approach that they call generational search, and that is simply analyzing the symbolic formula so that you can output an entirely new generation that should, each generation should be able to reach a whole new depth of the graph in every direction, essentially. And then they have a series of optimizations that are pretty hairy. Basically, it's something that it's probably best to go look at the paper in general. But to give you an idea of the power of some of these optimizations, like they'll do structural analysis of the code. So if you're inside of a loop, obviously, since this is a runtime analysis for us, we're taking this trace and we're encoding it as each instruction executed. And we don't currently do structural analysis on the code yet, just because we don't have the resources quite yet. But obviously, by analyzing the code and determining that there's a loop there, the constraints are going to be the same that are encoded in the branch logic of that loop, right? So that will eliminate significantly how much of this formula that you're passing off to a solver. And you have to understand that solvers are not fast. Like Z3 is fast for a solver, but solvers are not fast. They're slower than a pure software CPU emulator by far, because we're dealing with algebraic ranges of values as opposed to just writing to a register file, a memory file. That's simply a modification of memory. Like this is a real complicated problem. So it's very much CPU bound and being able to solve these formulas. So being able to do optimization on these formulas is a huge problem. And they're able to do things like analyze if this large formula that represents 1 million instructions, has constraints inside of it that don't actually matter to where you want to go in the code, and so on and so on and so on. So point is they have a whole lot of optimizations that are awesome. So what were the results of Microsoft investing in this? This was in the 2008 timeframe, as I said, before Windows 7. They have they have the primary research paper called Automated White Box Fuzzing, but they have a few follow-ups, tech notes, and things like that. They don't put a number to it. I know it's in the high multiple thousands, maybe 5-figure thousands. But basically what they do tell you is that about 1/3 of all file fuzzing bugs since 2007 were found with the Sage system. So that's pretty impressive. If you think back to 2007 and the number of patches that were coming out in Microsoft Office were just huge, that they switched over to an XML-based Office format purely to try to sidestep the problem of all the binary integer overflows that you were finding in the Microsoft Office format. So the fact that they found 1/3 of all the file fuzzing bugs in the internal testing time before they released Windows 7 and Office 2010 was a pretty significant deal. The things they learned from taking the generational approach is, well, number one, we're working with vulnerabilities that are a fairly shallow code depth. So when I mentioned 1,000 branches deep, that's still pretty shallow in the context of a program's execution. And what is interesting about the generational approach is, since the bugs are fairly shallow and we're able to generate a series of new inputs that it's equivalent to the number of branches that you took to get to that final state, it only takes a few generations to get to the full depth of the code graph that you're going to be able to reach. And obviously, one of the other things is that since we're generating symbolic formulas, and as I said, symbolic execution is fairly slow, we want to be able to get as close to the business logic and the parsing logic of the program as possible. We don't want to waste time trying to sort out what was the COM interface that then got you into the object that then got you down to the sub-library that's now doing your XML parsing. No, you want to wrap the library directly. So it takes a little prior analysis and a little bit of work to isolate and wrap the actual code that you're looking for. You can't just say, point it at Office and let it go. So we have our implementation, Mofo Fuzzflow. And we essentially tried to take the lessons that were learned by Microsoft and realize that this is something that is achievable based upon our research from last year and the Taint analysis and symbolic execution work that we did. And so our system is architected primarily around the BAP framework infrastructure, because, as I said, one of the things you need is the symbolic executor to have a semantic knowledge of what the code does. And BAP, bless those hearts at Carnegie Mellon, they've had a series of grad students encoding this logic for me in their tracers and program analysis engines for the last 4, 5, 6 years. And it's been a tool that I've used for about as long, so I'm very familiar with it. And so our tracer is a pin tool. As I mentioned before, the Dynamo Rio is a bit faster platform, but it's not fast enough for me to want to rewrite the entire translation from x86 to a BIL. So we use the pin tool. We've modified it pretty heavily, though, because we need the memory state at the point of a crash or at the point of the end of executions that we know when you're encoding this program logic, we can concretize, meaning rather than have a symbolic value at every reference, we can say, oh, was this mapped to memory? If it was, then we can actually put that literal value in there. So we collect memory dumps. The original pin tool didn't have any coverage information. We added input stream names. It also does our debugging function for us, so we don't need an external debugger. It could be argued that it might be better to use an external one, but we handle it internally. And then we have our own symbolic executor that takes the BAP IL, analyzes it, and converts it to our SMT-lib formulas that we pass off to Z3. Z3 being the solver that we use. I also mentioned that SDP supported, but Z3 has better performance. I'll be putting up a blog post a little bit that goes into detail about the different solvers and their performance and the realities of trying to replicate a system like this. And then we have just obviously our own custom tool written in OCaml that plugs on top of BAP. That's a standalone tool that I'll show you in a second that glues this all together and provides the interface for running the concolic testing. So, limitations. There's a lot of them, unfortunately. Once again, we don't have the crazy resources that MSR does to do a lot of optimization. So the taint tracer from BAP is not highly optimized. It's highly functional, and it's the best tool out there that we have available, that everybody has available. So I highly recommend using it, but it's not the most optimized code in the world. That's okay. This second line in here is actually not correct because last night, as I mentioned, I kicked off the analysis for trying to trigger the bug in LZ4, and that took a 5 megabyte input. So I was able to replicate a bug that took a 5 megabyte input for the first time, which is pretty crazy. But in general, we've been keeping this, we've been targeting libraries that take small inputs. And we've been crafting our own types of formats if necessary so that, you can take a larger container format, like a MP4 or whatever it might be, and simply encode certain parts of the logic, or even a PDF. You can put certain object types in there, and it does very, very well as long as you keep the original input size down to a minimum. Because once again, every byte, and I'll show you this in a second, every byte that gets mapped into memory becomes something that the taint trace needs to follow, and eventually becomes something that we convert into a symbolic expression of relationships and constraints that once you create a large enough data space that you're trying to track, it becomes computationally too expensive to have many iterations. So another problem is pin just design error, or not really error, but just a limitation, is that they're unable to flush basic blocks. So if you're doing a code coverage tracer, I would highly recommend using Dynamo Rio, because if all you need is the hit trace, if all you're interested in is the first time you visit a basic block, you can invalidate that code block cache, and it will go back to reading the native code. And so you essentially have the ability to remove your hook that was doing the callback to track the execution. Pin has the ability to flush all code blocks or none at all. That's just a real simple little thing. Our conversion from BIL to SMT-lib is fairly slow because, once again, BIL expands every x86 instruction out into micro-operations. So for every move or add, you actually have a series of maybe 8 micro-operations that are occurring, and a comparison or more complicated x86 instructions are even in greater so. So you have the option when you're writing a symbolic executor on whether or not to write very tight, specific code on how you want to translate this to SMT, or you have the option of going the easy route, which we did, which is pretty much a literal one-to-one translation that later on requires a heavy optimization layer that we haven't written yet. So our formulas that we generate are a lot larger than they need to be, and are representing the translation at a lower level that isn't quite as intelligent, or it's not producing optimized formula to be solved. Then, of course, the same constraint of needing to wrap libraries directly, and yeah, the whole, we don't have a bunch of geniuses to optimize a bunch of the formulas and do that structural analysis. Like, we can do the structural analysis. That's something I think that we'll be able to do in the next couple months. But there's a lot of design that went into their approach that we didn't take into consideration when we were writing our Symbolic Executor. So there's a lot of optimizations that we just simply don't have. So does it blend? Does it work? Let's flip over here. I'm going to have to mirror my screen, so just bear with me for a second. Okay. Oh yeah, here I am. I'm still running the. Let's kill that. I totally forgot to kick off my my other repro when we started here. Actually, so before we do that. Oh, good. Okay. So we're actually going to do this in reverse order. I'm going to show you the real-world example first. So we found a bug in libgraphite 2 using this technique. We spun up a couple of fuzzers on our fuzz farm to try to see the practicality of, did our approach actually work beyond what we were doing last year. And this is not the one. This is the one. So I started this off at the beginning. That's what you saw was running there. And what we're left with is a crash directory, which you can see is dated, today at, this is like Pacific Standard Time, I think. Can you see that? Okay, it's not too bad. Here, I can zoom in a little bit. All right, so yeah, you can see that these were all generated in like the last 30 minutes or so while I've been up here on stage. And this is the outputs that were generated by this command here. What we're doing is we're using Graphite 2.1.2.3's built-in test program called Compare Renderer. Its job is to take a font file and do all the parsing internally and make sure that everything goes well. And we use one of their inputs here. Here I can show you what normally the behavior would be before. So just got to get rid of this guy here. And so this isn't going to be exciting or anything. This is what the normal test looks like. Boom. Okay, does nothing really. But what we're doing is we're observing the execution of this program under our tracer, and we're generating these constraints and so on. And so at the end of the day, what you see is that we have the samples directory. These are the new inputs that were generated from observing the execution. So we can see that we generated somewhere like about 600, 700 new inputs in the 758 new inputs in the course of about a half an hour, just to give you an idea on how fast this is, not too fast. And then we've ended up with a series of crashes. And once again, these were all generated while I've been up here on stage. In fact, it looked like one was just generated here. So let's see, let's change the input to one of these files here. And then I'll take you through the basic example, which will be a little more obvious. But I just wanted to show you what this looks like. All right, so this is the most recent crash. We should see a core dump, okay. No file, what? Well, okay, so we can see that crash causes a core dump. Now let's show you in slow motion what this is really doing. We have that canonical example of this crash right here, where we're looking for the BAD exclamation mark as the input that we know will cause an exception, a crash, right? The little crashing function here isn't anything significant. It's just going to cause a null dereference. But what we want to see is we want to see the input change from so our input is going to be good, right? G-O-O-D. And what we want to see is an input that is changed to bad exclamation mark and trigger this crash. So we can do this real time because this is a real simple example. No, it's not the right one. And this is pretty much the simple usage of how you do this. You give it an input executable. You give it a seed file that it's going to take as the original input. This is just as what the taint tracer is going to interpret as the external user supplied data, and then arguments on how to use it, %s being the transliteration of the input file, and so on. So let's slow this down really quick before this gets too ahead of itself. So as we start the trace here, what's happening is this is the pin tool kicking off, running the program, and collecting the taint trace. We can see here that it's taking the original input file, it's outputting it to the samples directory as the first possible solution, and we can see that there's only 5 bytes in there, which is GOOD and a terminator. So it's reading that 5-byte buffer into memory. It's recognizing that that's a tainted value. It's generating a new mapping. Where'd that go? So it's generating these new mappings. These are internal tracking of each one of those bytes in memory, and watching as it goes through the execution of the program. So we'll go ahead and let that continue. It should only take maybe 30 seconds or so to get through this, because there was only less than a dozen branches in that original source code. And what we're looking for is you can see as it's like generating this samples / 12 solution, 14 solution. That's the 6th solution. Now this is all kept as a internal bit mask or bitmap, and so the bitmap represents what possible branches are taken in the total code graph. And so what we end up with is, these were from the previous run too, but we ended up with something like 20 different possible solutions. It ran them all under code coverage, and if we look at the crashes directory, we should have a brand new one that is 1143, 1142.59. So if we page up here, we'll see somewhere in there it'll say crash found, I think it was like the 13th input or something here. Crash found, I copied it over. The point is the contents of this file, as we would expect, would be BAD, right? And there it is. So this showed us going from the good inputs and symbolically evaluating the code, and determining that one of the inputs that are possible was a BAD that based upon the constraints in the code, and it generated that file, which led, of course, to the crash. So I guess if you want to see it actually trigger, you can see there, once again, we got a core dump. So that's the magic. So hopefully all that makes sense. And when you look at the slides here, I show a little bit of the graphite. Let me just get back up in here. So you can see here that graphite vuln. It's a real vuln. This code's all going to be available, so you can reproduce it yourself. The graphite vuln that we generated was actually a problem it's an unchecked malloc that you can see here. There was table_len that was taken from the input file. They tried to allocate it. We can see from the debugger that the size was like 3 billion. And so, of course, they didn't have 3 gigs of RAM to allocate for that, and there's 3 terabytes of RAM to allocate for that. So the unchecked malloc ends up with a null table pointer, and we try to f-read into the null pointer, and we just get a crash. So that's a legitimate bug. We haven't reported it yet. It's not really useful, but you can go out and check this out yourself and play with this code. So I'm at 50 minutes. I know I have like 10 extra minutes, so I'm just going to do a really, really brief overview here, because essentially my initial thought was that we can take the same approach, semantic understanding of code, that we utilize in our process and apply that to binary differencing. And theoretically, this is possible still. But so far, I have to admit that the last 2 months of my attempts have not been fruitful. So first, let's talk about the problem of bin diffing. Essentially, 2004, bin diffing became fairly popular because Halvar and Rolf and a couple others were the first to apply isomorphic graph comparison to the problem of binary differencing. So this is the same technique that you would use to compare graphs for similarity. It's a similarity index of the structure of a graph. And it's used now commonly for malware classification, and it can also, of course, be used in tools like bindiff or binnavi to see similarities of code graphs. Now, these were the good old days because the locality of the vulnerabilities were the actual bug, like an integer overflow, which was the most common, second most common bug in 2006. So, this was the heyday for integer overflows. Like I was saying, those file format bugs and Microsoft Office file formats and so on, in COM objects, all kinds of stuff. There were a ton of integer overflows. The nice thing about an integer overflow is when you cause a malformed when you cause an integer overflow to occur, it's typically used very close by in either an allocation or an array index or something like that. There's not a huge gap of space going on typically. I mean, in theory, yes, you could store this malformed value into an object and have the object passed around to a series of function calls and later on referenced. That does happen, but most of the time the locality of the bug is very close to what the root cause was in the case of integer overflows. 2014, we are looking at a whole lot of use after free bugs. And use after free bugs are really easy to identify in a patch. They add a reference counter that was missing, and then that's what you're getting. You're getting the location of the free being tracked. What you're not getting is the relationship of the code that allows you to exercise this free to object later on and take advantage of that use after free. So here's another little snippet saying 2008, use after free now dominates as a class in web browsers and document parsers. Here's what inline bounds check, and this is actually Heartbleed, but this is what the changes look like. It's pretty straightforward. A size check is added here on the left block in the process heartbeats block here for a certain size, and if it's greater than or less than, you take a different branch, and that's really, really easy to see. And once again, you would be triggering this bug very close to where you could use the bug, or where the bug was caused. Use after free, we see changes here. Once again, it's fairly easy. You can see at the bottom there is a call to node add reference, and that's where they fix the bug. Unfortunately, where you trigger the bug and take advantage of the bug somewhere else is not at all in the same function, typically. So there's, once again, I'm just going to kind of skim over this. It's something you can look at if you're interested in on the slides, but I don't want to run into the next person's time. But there's several algorithms that are in place in BinDiff that try to find the similarities between functions. But the problems are that there's still a bunch of mismatched functions. Like, to give you an idea, we BinDiff all the patches that Microsoft and Adobe put out, and it's not uncommon to have BinDiff report 1,000 changed functions in a single patch. This is clearly not actually correct. It's a whole lot of false positives. And one of the main problems with that is that they haven't kept up with compiler optimizations. They are not aware of chunked functions because IDA doesn't handle them very well. The heuristics that are inside of BinDiff are sometimes applied in the inappropriate order, and it's not configurable, or you're not able to give a weighting to how much value you want to put into a particular heuristic. And then, of course, the eponymous problem with x86 code being that, the code and data problem, IDA oftentimes misidentifies data as code, and then, of course, thinks that that's a modification to the binary. So, and even in the case of something as simple of a heuristic that we identify just visually, is that you can see each one of these on the left and right are functions that have the identical number of instructions, and it couldn't even determine that those were actually 100% matching functions. There's no change to the function whatsoever. But due to the misapplication of the order and the order of the heuristics that are inside of it, it has a heuristic that matches this early on, and then later on uses a different heuristic that is completely incorrect and misidentifies them. So we came up with a tool. I had some of my guys work on this tool to do a set of heuristics while I was working on the semantic understanding. And just to briefly go through, we add a bunch of stuff to the BinDiff database, and it's aware of the safe-int or int-safe libraries. It's aware of the types of changes that addref and things like that do. And it has a set of 6 heuristics in it. So here's real-world results right now. This is something we'll give out for free as well pretty soon. So here's an example. BinDiff says 179 functions have changed in IE install and MS13097. We could filter out about 35, 36 of those, so it's a 19% reduction. Word convert, MS14017, we were able to see a 76% reduction. So, we got it down to 13 functions instead of 55. So that's something that we could get done in an afternoon, no problem. In Erlmon, MS14035, there was 31 reported. We got that down to 22 for a 29% reduction. MS14035 got it from 543 functions. When we see a patch that has 500 to 1,000 changed functions, we're just well, screw this. We need an automation system for that. It's not really worth our time to go through and look at every one of these changed functions and then try to also look at the call graph that can reach these functions to determine if there's an exploitable path here. Or it's not even just these single functions that we're looking at. We're looking at the functions that reach them to see if this is the root cause for a use after free bug or something like that. So we're in the space of this is crazy. Now here's a really good success story. Adobe's CVEs tend to have a lot of churn, and according to BinDiff anyways. And so we were able to drop this from almost over 1,100 changed functions down to 143. Still a whole lot of changed functions, still something we need to post-process with a more intelligent engine that does the semantics. But that analysis is going to be slow when it does work anyways. So being able to drop it from 1,100 functions to analyze down to 143 is still pretty good. So just briefly, the idea behind the semantic engine is that we will still see problems no matter how good heuristics get with register reassignment, branch inversion, using different optimization flags so that it's using different series of instructions to represent the same semantics of code. So at the end of the day, a syntactical comparison or a structural comparison is never going to do the complete job. So since we've been able to show, in fact, last year we had a slide in our deck that kind of gave an example of what solvers can do. And one of the questions we asked the solver was to look at more or less obfuscated code versus a very obvious one-line snippet. And so in the bottom here you see add EAX, EBX. And then on the right you see a series of instructions that look more or less equivalent. We got add EAX, EBX, then we null out the EBX. We subtract something from ECX, which we don't care about. We set a flag, BL, and then we add the nulled EBX to EAX once again. So the question is, are those equivalent at the end of the day? And so we converted that into SMT-lib. We asked the solver to tell us if there was a possible input to the code snippet that would end up with a different ending register assignment. So in this case, in that blue line, that was the condition that we're asking it about. If the bit vector addition, so in SMT solver, something that I didn't really talk about is you work in different domains of number theory. So you can talk about real numbers or integers or bit vectors or what have you. It commonly makes sense to talk about bit vectors since we're talking about bit space and x86 code. And so in any case, we're asking at the very end if an addition between EBX and EAX is equivalent to this entire other upper portion of the code snippet. And the red line is the lines that represent the only two instructions that might not be obvious. Obviously, EBX added to EAX and then adding 0 once again to EAX isn't going to change anything. But those two other instructions do, in fact, produce an alternate result if ECX is 123 because it's looking, it'll set a flag to 0 or 1 it'll set a flag to 1 based upon if the lowest bit of EBX is 0 or not. So in any case, having given this example, we had already shown to ourselves that it's feasible that we can compare two series of instructions and try to get the solver to tell us if they're equivalent or not. The strategy is basically you would take an entire function and mark the parameters as symbolic and basically iterate over every possible path that you could take, just like we do in our Sage clone. And for each one of those paths, we would ask it to solve the possible inputs that would reach every condition constraint that are represented. And at the end of the day, the resulting register state and memory state should be more or less equivalent. But as I said earlier, this so far has not panned out because we do not have a high enough IR that is not tied to a register and memory model specifically. So this has been done by Dawson Engler, apparently. I found this only like 2 weeks ago, well after I was already down this path. And they have taken a source code-based approach with CLI, and they annotate the code. They do a very similar process of marking the parameters as symbolic. The way that CLI works is it actually forks the process, so you get the identical memory model. And it also works at a higher level. Since it's working from source code, it works and it has symbols available. That's the big thing. It's able to use symbols as indirection instead of having a discrete memory model. So it knows which variables are pointing to which memory addresses, and we don't. We don't have unique names for those memory variables right now. So hopefully I'll be back next year, and this will be a much better topic. But basically, hopefully what you're going to take away from this is that, number one, all this code's available, so you should check it out. Number two, there is a more determinate method of doing fuzzing. And it's hard to even call it fuzzing anymore. It's automated test generation, because this is not really a fuzzy approach. It's an approach based upon a sound process of observing the program, observing the conditions, watching the data propagate, and passing it off to a solver to reason about the values that are possible, that should be the inputs to reach different states of the program. So with that, say thank you for your time. Hopefully you enjoyed the show, and I'll take any questions. Yes, Sergey. Do we want to get the mic?
he attributed to something. How is Adobe code different to that?
Oh, well, in the patches, on the Adobe patches, they just use, I think, different compiler flags than, I mean, obviously they have their own heap manager. They use their own different compiler flags than Microsoft. I think bindiff was tuned mostly for Microsoft patches. So we've observed pretty good results, I think, with Adobe versus Microsoft, just because they're so different. So our heuristics can find a lot of those changes pretty easily. Yeah, they use different compiler settings, I would say. But Microsoft, one of the things that they've done that's a significant problem is they have a lot of chunked functions. Chunk functions are, for anybody else not aware, is when the compiler identifies that the tails of two different discrete functions are similar. So the code at the end of two different functions, it can be shared and output by the compiler. So you get a long jump from the body of one function to this kind of isolated stub that's at the end of a function. So two different functions will do long jumps to that same stub. So they save a couple of bytes at a time or something like that and make it really a pain in the ass for IDA to disassemble. But any other questions? No? Okay. Well, the VRT has a blog. You can check it out, and I'll be writing up a blog post on the LZ4 bug, and I'll be announcing the code release, which I'm kind of on the hook to release it by June 30th, so you'll see it out there in a couple days. And I'd just like to point out that this is not all just the work of myself. Paul Janik, he's no longer with the team, but that's Packet. He was here with me last year. Excellent guy. And so he did a lot of work with me on the OCaml side especially. Ryan and Marcin are two of my guys that do a lot of work on the bindiff stuff. And we have Eve. He's actually here. Some of you I know him. He's our mitigations expert and code source analyzer. And so great team. And we're also going to be hiring 3 more guys over the next year. So talk to me if this is the sort of thing you're interested in. Once again, thank you.